Micro and Nano Manufacturing. Me 474. Module 5. Part 1. Presented by Jithu John, Assistant Professor, Department of Mechanical Engineering, Government Engineering College, Kozhikode. 4. 8th semester. B.Tech, Mechanical Engineering. APJ Abdul Kalam Technological University, Kerala. Micro and nano fabrication. The philosophy is to fabricate and fit more and more electronic devices into a smaller workable area. We could increase the performance of ICs by placing transistors closer together and by depositing transistors in a precise way. Traditionally, ICs have been manufactured by use of microfabrication techniques. Figure 1 shows the memory and minimum feature sizes for dynamic random access memories, as a function of time. Figure 2 shows a single strand of human hair and an array of transistors on a single piece of silicon, revealing the relative size of transistors that can be accommodated on a piece of silicon. Microfabrication. Microfabrication begins when a set of photomasks are provided to fabricator. A silicon wafer provides the basis of the integrated circuit. The wafer is insulated by growing a thermal oxide layer. A conducting layer is deposited that is used for producing transistors. Depositing techniques: sputtering, PVD using a magnetron, metal oxide CVD, molecular beam epitaxy, and chemical beam epitaxy. Individual resistors are deposited to the wafer by use of photolithographic techniques. Further processing, pattern transfer, etching, deposition, and growth. Epitaxy refers to the method of depositing a monocrystalline film on a monocrystalline substrate. The deposited film is denoted as epitaxial film or epitaxial layer. The term epitaxy comes from the Greek roots. Ap means above. Taxis means deposition in ordered manner. Epitaxial films may be grown from gaseous or liquid precursors. The substrate acts as a seed crystal. The deposited film takes on a lattice structure and orientation identical to those of the substrate. Figure 1.3 shows the standard route followed to produce an integrated circuit. The same flowchart can be used for producing any microscale product made with silicon-based materials. The chart shows the basic functions of initially cleaning the substrate, applying a thin film using many deposition techniques, applying lithographic techniques to apply mask material, etching to form the required shape of the microscale features, removing the mask material using chemical or plasma etching, and finally characterizing the nature of the created structure. Fabrication at the microscale is made up of three basic regimes: addition, multiplication, subtraction. 1. Addition. The addition phase involves adding a thin film coating to the substrate material. By electroplating or spray coating a liquid film to the substrate and allowing it to dry. A thin film can also be created by oxidation or doping in an atmospheric chamber. By fusion bonding a solid to the substrate or using low and high pressure vacuum techniques to bond a thin coating to the substrate. Figure 1.4 shows microfabrication by the addition of a thin solid film. Example of microfabrication by the additions are: in liquid state, electroplating, spray coating; in atmospheric state, oxidation, PECVD, doping; in vacuum state, LPCVD, evaporation, PECVD, sputtering; in solid state, bonding or joining. 2. Multiplication. A process step necessary to create microscale features, particularly channeled features that are used in micro and nanofluidic devices. It can be done by direct writing of features using electron beam, ion beam, and atomic force microscopic techniques. Contact lithography is another popular technique for depositing features. Micro or nanoscale feature generation using microstamping processes. Figure 1.5 shows microfabrication by the multiplication of a thin solid film. By photolithography. Contact. Projection. By direct write. E-beam, ion beam. AFM. By microstamping. Molecular films. Transfer of masking or structural layers. 3. Subtraction. It can include mechanical micromilling, laser ablation, water micromachining. These processes can remove materials at much higher material removal rates. Figure 1.6 shows microfabrication by the subtraction of parts of a thin solid film. By liquids. Chemical reactions. By gases. Chemical etchants. By focused beams. Ion mill. Excimer lasers. By plasma. Plasma chemical etch, sputter etch. Reactive ion etch. By mechanical. Chemical or mechanical polishing. Basic chip making process. 1. Steam oxidizes surface, red layer. 2. Photoresist, dark blue layer, coats oxidized wafer. Performance has improved with the growing use of wafers having a buried oxide layer or those fashioned to have thin layer of strained silicon at the top, or by employing both techniques at once, as shown here in this figure. 3. Lithography transfers desired pattern from mask to wafer. 4. Chemicals and baking harden unexposed photoresist. Other parts of photoresist are removed. If modern techniques such as optical proximity correction are applied to compensate for the blurring effects of diffraction, photolithography can create features smaller than the wavelength of light used in projecting the pattern. In this example of optical proximity correction, a complicated pattern used for the mask, on the left, results in crisp features on the chip, on the right. 5. Chemical etching selectively strips off the oxide where no photoresist protects it. The rest of the photoresist is removed. 6. Ions shower etched areas, forming source and drain junctions. As feature sizes shrink, removing photoresist and residues that remain after etching becomes difficult, as shown in the left figure. But supercritical carbon dioxide can penetrate tiny openings and dislodge particles without leaving traces of cleaning fluid behind, as shown in the right. 7. Metal contracts are added using lithography during later stages of fabrication. As shown in figure, as many as 8 levels of wiring now connect the millions of transistors found on a typical microprocessor. Aluminum, the metal long used for this purpose, has given way to copper, which is more difficult to emplace but improves the speed and integrity of the signals carried on the wires. Once again, look at the chip making process step by step. 1. Steam oxidizes surface. 2. Photoresist, dark blue layer, coats oxidized wafer. 3. Lithography transfers desired pattern from mask to wafer. 4. Chemicals and baking harden unexposed photoresist. Other parts of photoresist are removed. 5. Chemical etching selectively strips off the oxide where no photoresist protects it. The rest of the photoresist is removed. 6. Ions shower etched areas, forming source and drain junctions. 7. Metal contracts are added using lithography during later stages of fabrication. Intel chip making process. The making of a microchip. Intel.
The world is producing data at an unprecedented rate, faster than our ability to analyze and understand it. To move, store, and compute all of this data requires incredible processing power. From the blazing speeds of our devices to blazing trails within AI, Intel builds chips that are at the heart of nearly everything. Within every Intel chip manufacturing facility across the globe, innovators are pushing the limits of science and literally rearranging atoms to create groundbreaking technology. This strong silicon foundation is what gives each Intel chip limitless potential. At the heart of all modern electronics, the transistor is a tiny switch, 10,000 times smaller than a human hair, that controls the flow of electrons through a circuit. To build a processor, billions of transistors are packed into an area no larger than a fingernail. It's one of mankind's most complex feats, and a remarkable achievement that Intel has essentially doubled transistor density in every new generation of processors. The process begins when silicon-rich sand is melted and cooled, forming a solid, which is then sliced into wafers. Once inside an Intel fab, the raw wafers begin their long journey through an incredibly complex process. They're loaded into front-opening unified pods, or FOUPs, which travel hundreds of miles along Intel's automated superhighway, going from tool to tool, as processors are painstakingly built up on each wafer. The wafer first goes through a series of important steps, such as photolithography, ion implantation, and etching, that prepare it for the critical transistor formation process. Intel was the first to manufacture three-dimensional transistors called FinFETs. FinFET construction requires first building a channel in the form of a fin. Intel has devised several innovations to overcome fundamental barriers to continued transistor scaling. One such innovation is a breakthrough fabrication method called gate last. It involves building, then removing a temporary gate in order to precisely place the dielectric material and metal gate. This allows for the gate to wrap around the fin and control the flow of electrons through the channel. Another invention moves the transistor contact directly over the active gate. To accomplish this, the gate material is recessed and then filled with insulating dielectric material to prevent the creation of a short circuit. Next, the dielectric near the gate is etched, filled with metal, recessed, and capped to allow a novel self-aligning process that enables the high-density contact geometries. Now, the dielectrics are etched selectively to expose only the desired part to connect to the first metal lines. This is done through an innovative via etch and deposition scheme, allowing contact over active gate to happen. Finally, dozens of layers of metal interconnect lines are added to complete the circuit. After more than 1,000 of these complex steps, the wafers are finally prepared for singulation and packaging. Innovative processor packaging has become a critical feature of advanced computing architecture. 2D and 3D packaging technologies are enabling new device form factors and additional boosts in performance and energy efficiency. Testing of the final product ensures that every chip exceeds our performance and quality standards. In addition to adding more performance and features with each new processor generation, Intel's integrated design and manufacturing capabilities have enabled humanity to innovate game-changing technologies that
Nanofabrication. The challenge for nanofabrication of these devices is to deposit materials in a physical way that will faithfully reproduce device function. A very simple and novel way of reproducing nanoscale features is soft lithography. Nanofabrication using soft lithography. A liquid known as polydimethylsiloxane, PDMS, is poured onto a master pattern of the feature to be produced. The liquid cures to form a rubbery solid that can be peeled over the master pattern. Fabrication of field effect transistors using the soft lithographic known as micro-contact printing. Soft lithography, producing an elastic stamp. Figure illustrates the principle of the soft lithography technique. 1. A liquid precursor to polydimethylsiloxane, PDMS, is poured over a master stamp. 2. The liquid is cured into a rubbery solid that matches the original pattern. 3. The PDMS stamp is peeled away from the master. In the self-assembly process, a stamp is coated with a solution of molecules known as thiols. Thiols then self-assemble on contact with a thin gold film that has been deposited to the silicon substrate. Figure shows the basic principle of the process of micro-contact printing of a self-assembled monolayer on a gold film. 1. The PDMS stamp is coated with a solution consisting of organic molecules called thiols and then pressed against a thin film of gold on a silicon plate. 2. The thiols form a self-assembled monolayer on the gold surface that reproduces the pattern. Features in the pattern are as small as 50 nanometers. In micro-contact printing, a PDMS layer is used as a stamp. The PDMS layer is first soaked in a molecular ink and then brought into contact with a substrate in order to transfer the ink onto the substrate surface. In micro-contact printing, only the ink from the raised surface of the PDMS stamp is transferred to the substrate. Various inks, including small biomolecules, proteins, or suspension of cells can be used. Figure illustrates the fabrication of a PDMS layer incorporating microstructures. Drawings A, 2, D correspond to the fabrication of a rigid master via photolithography. Drawings E and F can be considered as part of the soft lithography process. The process has also been used to deposit GaAs and AlGaAs to silicon substrates to produce nanoscale transistors. Figure shows the schematic diagram of a GaAs or AlGaAs field effect transistor produced using soft lithography. FET fabrication soft lithography. The procedure for fabricating a set of field effect transistors, FET, involves defining the resistive contacts and the alignment tracks by micro-molding in capillaries using polyurethane liquid. The second process involves curing the polyurethane and then peeling off the PDMS mold and removing the polyurethane base layer using the oxygen R.I.E. reactive ion etching process. The ohmic contacts for source and drain are produced by evaporating ONIGE to the surface and removing the remaining polyurethane. Once annealed, the etch trenches are defined by etching with citric acid and hydrogen peroxide. The gate is then produced by evaporating a thin CR or O layer onto the surface. The product is a set of nano-structured field effect transistors produced using soft lithography processes. Schematic illustration of the procedure for FET fabrication. A. First mimic using polyurethane, PU, to define the ohmic contacts and alignment marks. B. Cure PU, peel off the first PDMS mold, and remove the PU underlayer using oxygen Re. C. Evaporate LNIGE, lift off PU, and anneal to form the ohmic contacts for the source and drain. D. Register, second mimic to define etch trenches. E. Cure PU, peel off the second PDMS mold, and remove the underlayer using oxygen Re. F. Etch in citric acid and hydrogen peroxide solution to remove the 2-degree angle in the etch trenches. G. Register, third mimic to define the gate. H. Cure PU, peel off the third PDMS mold, and remove the underlayer using oxygen RIE. I. Evaporate CR/O and lift off PU to form the gate. J. Cleave two ends to remove the 2-degree angle in these regions. Figure 1.24 shows the physical layout of the field effect transistors produced using soft lithography process. Micrographs of field effect transistors with various gate lengths L and gate widths Z fabricated by soft lithography. References.